um, what is an introduction to gravitational waves and the observations of gravitational waves. Um, and I hope I can also be there in person sometime in the future. Um, so my understanding is that this talk will just give an overview of gravitational wave observations. I think my colleague Joe Betzweiser will give a more detailed description of instrumentation and detection. And Shushant, who is there, I think will be also going through some analysis of real LIGO data, which I think is very exciting. So so I will try and talk about all this context around these other presentations. Okay, so when we observe gravitational waves are emitted by the motion of very dense objects, and these dense objects have to be very massive, and so therefore the best sources are very far away. And because we're looking at these dynamical motions of these very dense sources, that's why I call it the cosmic ballet, because it's like the cosmic motion of all these sources going around each other. Oops, hang on. Right. So this is the outline of my talk. I will just give a brief introduction of gravitational waves as a source and its detection. I will talk about the first detection of gravitational waves. And the first gravitational wave detection has this event label called GW150914 because it was detected on the 14th of September in 2015. And then we also want to talk about this other very exciting event, which is actually the first observation of gravitational waves from a binary neutron star, but it was also observed in many other wave bands. So in X-rays, gamma rays, optical wave bands, and so on and so forth. And this is GW170817, so observed on the 17th of August in 2017. And then I will just give a very brief summary of the latest observations and sort of wrap up my talk. I'm just one person talking here, but as already mentioned, I'm a member of the LIGO Scientific Collaboration, and we need multiple detectors, which I will explain in a moment. But we need multiple detectors to observe a gravitational wave signal, and so we need our partners in Europe in Virgo, and also our partners in Japan in Kagra. And as you can see, the work presented here, the first detection had a paper that had 1,000 co-authors, and then the multi-messenger detection had a paper and many papers which had more than 3,000 co-authors. So yeah, this is work of many, many, many people. Okay, so I said that gravitational waves are from cosmic sources. Why is that? So when we measure gravitational waves, we are measuring what's called the strain sensitivity, the strain amplitude, okay? And this is a strain caused by the motion of material and the quadrupolar moment of inertia of that movement. So H is the strain, and you can write down very roughly the strain. So this is what we're measuring, is a function of the gravitational constant g, the speed of light c squared, the mass of motion, the moving mass that causes this quadrupolar moment of inertia, and then the signal that we see is inversely proportional to the distance, and it's inversely proportional to the distance because we're measuring amplitude and not intensity. So that's one sort of difference between gravitational wave astronomy and typical standard EM astronomy, because we are inversely proportional to distance and not distance squared. Okay, and then the last factor is the ratio of the motion of the masses, the velocity of the motion of the masses, divided by c all squared. So if you just look at the numerical portions of this, you will see that g is 6.67 times 10 to the minus 11. And then c squared is basically 10 to the 17. So this is a factor of 10 to the minus 11 times 10 to the divided by 10 to the 17, and so you have a factor of about 10 to the 38, roughly, 10 to the minus 38, sorry, in the beginning, that you need to overcome. Okay, so you can already see, because of these factors here, these very natural constants here, that you need a lot of energy, a lot of motion, a lot of matter moving um, to make enough, generate enough energy to cause some strain H that is detectable on Earth. Okay, and this factor at the end here, you are only limited to 1, and so you want the v, the velocity of the motion, to be as close to the speed of light as possible, because you want this factor here to be as close to 1 as possible. So yeah, if we just put in some standard numbers for the mass, so let's say we have a 1-ton steel girder in the lab rotating at 1,000 hertz or something like this. And your detector is just 1 meter away because it's in a lab. Your strain amplitude H corresponding to this experiment is actually 10 to the minus 47. Okay, if you just plug in these numbers in here. On the other hand, if you take 2 black holes, and these black holes are 10 times the mass of the sun, so 10 solar masses, and these black holes are going around and merging, and even though they are 100 megaparsecs away, right? They're 100 megaparsecs away, so much further than 1 meters. The mass of these black holes, is 10 to the 30. The mass of the sun is 10 to the 30 kilograms, and so these 2 black holes are 10 to the 31 kilograms effectively. Okay, and that significantly overcomes this factor of g over c squared, and so you get a strain amplitude, even though it's very far away, corresponding to 10 to the minus 21. So as you can see, that's why at the moment, with the strains that we can observe, which are typically 10 to the minus 21, we are using gravitational waves mainly for astronomy and astrophysics, okay? Because we need these supermassive objects way out there to observe gravitational waves. And we don't have detectors that are sensitive enough to these kinds of gravitational waves just yet. So gravitational waves is not quite a lab experiment at the moment. Okay. Now, for those who are unfamiliar with gravitational waves have 2 polarizations. It is a strain force, so it is stretching and squeezing. So let's just take the first row here. And so, let me step back a bit. So the 2 polarizations of gravitational waves are the plus polarizations and the cross polarization. Okay, and so if you take the first row in this diagram, then as the gravitational waves travels into the screen, so just imagine the gravitational waves is traveling in the direction that's directly perpendicular to the screen, right? Then at one moment, it will stretch in one direction and squeeze in the other direction, as you can see. So the circles, the empty circles, are a reference for the rest locations of these. And so they're stretched here and they're squeezed here, and then it's returned back. And then at a later time, it is squeezed in that direction and stretched in the other location. So if you like, there's an animation here that says that, the gravitational wave is squeezing and stretching like this. So this is the plus polarization, as you can see, because the stretching and squeezing directions is, if you like, a plus shape. And then similarly, you have the cross polarization, where the stretching and squeezing is on the diagonal of this, okay? So that's what it means to have the plus and the cross polarization in gravitational waves. And if we just take one of these polarizations, so here I have, again, the drawing of the stretching and the squeezing of the plus polarization, and we compare it to what it does to just your standard Michelson interferometer, okay? So here we have a Michelson interferometer, and you have a laser. It goes to a beam splitter, so that half the laser beam goes in one direction, the other half goes in the other direction, okay? And then you have mirrors at the end, and then the mirrors reflect the light, back to the beam splitter, recombine, and then reflected to a detector. And the detector here is symbolized by the eye, but don't look at lasers with your eyes, of course. Okay. So at this point, you can see that if in this configuration, when you go from here to here, then this arm, right, is stretched, and this arm of the interferometer is squeezed, okay? And then later on, when you get to this configuration, this arm of the interferometer is stretched, and this arm is squeezed, okay? And as a result of the stretching and squeezing, then effectively the time of travel of light down the arms has changed. And so, for example, in this configuration, you would have constructive interference, so you have a bright spot. And then in this configuration, you will have destructive interference and you have a dark spot. Okay, and that's basically the principle behind how a gravitational wave detector interferometer works. That you have this stretching and squeezing, changing the light travel time down the arms, and that leads to a change that's observable at the detector. And that change is a function of the strain amplitude. Okay. Now, this is a very simple way, and Joe will show you that there's lots of many other bits and pieces that you need to make a laser interferometer gravitational wave detector. But the principle stands that this is the principle behind how a gravitational wave, a laser interferometer gravitational wave detector works. And the strain that we see, by the way, is delta L, the change in the length of the arm, divided by L, which is the arm of the interferometer. Okay, and so the arm of the interferometer for LIGO, for example, is 4 kilometers, or if you like, roughly 10 to the 3 kilometers, 10 to the 3 meters, excuse me. Okay, and so any change here is divided by that number, and so you want as long an arm as possible to be able to see as short a strain as possible, as small an h as possible. Okay, just based on this particular principle. So if we lasers, interferometers has this arm length. Oops, sorry, actually I had arrows, I forgot. Okay, and we can see that this is an aerial satellite shot from Google Earth of LIGO. This is LIGO in Livingston in Louisiana in the US. And so the laser and the detector are actually in this building, the central building here. Okay, and it's all very close to each other. And then you have 4 kilometers going all the way to here, which is where one mirror is situated, and the light bounces back again. And then you have 4 kilometers down the other side and bounces back again. Okay, and then it combines in this building. Down this line, I should say, they are evacuated tubes. So it's a vacuum, basically a large vacuum chamber that's 4 kilometers in this direction and 4 kilometers in this direction. Okay. And that's basically how the principle. You have the stretching and the squeezing of one of these arms, and then we see a change in interference at the detector, and we convert that to the observed gravitational wave signal. And so this is LIGO Livingston, which is here. And then there are 2 LIGO detectors in the US. So this is LIGO Hanford, LHO. Okay. And I mentioned there's Virgo. This is the Virgo detector, which is operated by a mainly French-Italian collaboration. It's situated just outside Pisa in Italy. There is Geo detector, which is really quite small nowadays and is mainly a test facility. So Geo only has 600 meters arm length. There is Kara in Japan, which is in the mountains, okay, in the Kamioka Mountains, where there are also the Kamioka, Super Kamiokande, for example, the neutrino detectors. They're all situated in the same mountain. And then there's LIGO India, which is being constructed. Oh, I should not say because I forget the name of the location. Anyway, it's roughly that location. So this is the network of gravitational wave detectors that we have, and one upcoming. And we need these detectors just to check that firstly, at a very basic level, to ensure that the gravitational waves are from the space and not from local noise. Okay, so local noise is uncorrelated between multiple sites, but gravitational waves, they travel through Earth. The Earth is transparent to gravitational waves, and so they can be correlated between these multiple detectors across the globe. Okay, just very briefly, I don't want to talk too much about this, but I just want to show you that this is the noise curve of gravitational wave this is the theoretical noise curve of a gravitational wave detector, one of the LIGO detectors. Okay, the black curve basically is the estimated sensitivity from all the known sources of noise. Known sources of noise, the model sources of noise are all these colorful lines underneath. So we can only observe signals that occur in this regime above here, okay? And you can see that the estimated strains that we can see are typically 10 to the minus 23. So with detectors, the gravitational wave amplitudes that we can see, we actually detect are of the order of 10 to the minus 21, 22, 23. Okay. All the noise sources here, I won't read them off, but I'll just highlight there are things like quantum noise, there's seismic noise, there is different kinds of thermal noise, different due to the material properties of the mirrors, of the coatings, of the very ultra high reflective coatings, and so on and so forth. So, and I think Joe will probably talk about these things and how to overcome these noise sources in his talk tomorrow. But yeah, just so bear in mind that we are looking at things about 10 to minus 23. The other thing to bear in mind is that the more massive the object, the lower frequencies they are observed at. So the more massive binary black holes, for example, they're observed at these low frequencies, and the higher the less massive a binary, so the binary neutron stars, for example, they are observed at higher frequencies. There are reasons for this, but there's a good rule of thumb to remember. And if you think about it a bit more, then there should be a lot of stuff in space, and indeed there is. Okay, so what we see here, what I just shown you, are the ground-based interferometry sensitivity bands between about 1 hertz and 1 kilohertz. So just this band here. But there is the LISA detector, which will be observing around the millihertz. There's pulsar timing array, which recently observed evidence for signals from supermassive black holes in this frequency range. And then there are probes that look for basically the cosmic microwave background equivalent of gravitational waves, so the relic gravitational waves from the Big Bang. So there are a whole spectrum of sources, as you can see. We are mainly talking about coalescences today, binary neutron star coalescences, but there are other things like supernovae and neutron star, spinning neutron stars, and so on. And just to highlight, all the observations we are talking about today is just a small part of the gravitational wave spectrum. Okay, we have seen things observed by pulsar timing. We hope to see many, many things when LISA is launched. The space-based detectors are launched in the 2030s. Okay, and so there's a lot of stuff to come. And today, even though I can talk for a very long time, we are only talking about a small portion of the entire gravitational wave spectrum. Yeah, and even in that small portion of the gravitational wave spectrum, I will only talk about compact binary coalescences, okay? Because those are the main sources, those are the only kinds of sources we have seen so far. These are binary neutron stars or binary black holes that are spinning around and merging, okay? You can also have gravitational waves from supernovae, from mountains or lumps or even pimples, if you like, on neutron stars, just very, very small bumps, asymmetries in neutron stars that are rapidly rotating. And again, you can have the cosmic, you can have the Big Bang's relic gravitational wave imprint, which will be correlated, although correlated as correlated noise, gravitational wave noise from multiple detectors. And again, we are only talking about this today, and there are other things we can talk about at a later time. Okay, so let's talk about the first detection. And the first detection, it looks like this. This is GW 150914, as we like to call in the group, in the field. So this is the signal from the Hanford detector, and this is the signal that was observed by the Livingston detector. Okay, and really this is very much just like the observed signal. You only have a bandpass filter. So this is the output from the detector, except that you just make a little filter that cuts out the low frequencies, the frequencies, and the very high frequencies. And you can already see this very nice inspiraling signal, okay? And then if you clean up the signal even more and try and get the best fit model signal, you get something that looks like this. And I will talk about this in a moment, but just to highlight that the signal, if you just take the Fourier transform and in small chunks of time, and you can see as time evolving, that the strength of the signal goes from low frequency and then to high frequency. So this is what we call the chirp. You see it's a whoop kind of thing, except it's not actually quite that frequency. But you can see that this again is this very distinct chirp. And so this is how hopefully it should sound like. I don't know if you can hear this, but let's see. So this is the um, this is so you're, if you can hear this, and I don't know if you can hear this, but assuming you can hear this, there are two versions of this. So one version is the low frequency unprocessed sound of this gravitational wave, and the other one is a higher frequency which is shifted so that it's more easily heard by the ear, so it's more in the audible range. But if you listen closely to the first version, and I hope you can hear it, it sounds like a thud. Boop. Okay, that's what the gravitational wave actually sounds like, boop, because it's a very low frequency. It's about 100 hertz or so. Let's try again. Oops. Um, yeah, so I hope you can hear that, and it's just a very very low thud is how it actually sounds like. Okay, so what was very nice about this signal as well is that it was a very nice coming together of theory, lots and lots of years of theory, and lots of years of analysis. Okay, so the red line is basically what's predicted by taking Einstein's equations from Einstein's theory of relativity, taking Einstein's equation and crunching the numbers as the black holes evolve and go around. Okay, and so you get a prediction that is the red line, and the light gray line is what the data is. This is the best fit correlated data from two detectors, because we want to correlate multiple detectors, because that is those two detectors see the gravitational waves. And you can see that the light gray overlaps very well with the red, so the data overlaps with the theory very well. And what's more, if you make an assumption that the signal is from two binary black holes going around each other, then you get the more constrained version, which is the dark gray version, and that also um, um, corresponds very well to the theory. So everything says that the modeling, this model points to basically two black holes, one 36 times the mass of the sun, the other 29 times the mass of the sun, and they're in spiraling, so they're going closer and closer at this phase, and as they get closer and closer, the gravitational wave emissions frequency gets higher, faster and faster. So that's why you get this whoop sort of thing, and eventually they merge around here, okay, and then here this ring down, this sort of oscillatory phase, is actually the excited black hole sort of being ringing down like you would a bell. It's radiating gravitational waves, losing energy, and it's just a black hole that's ringing down. Okay, and so this is a really fantastic result, because firstly, it was very easily seen in the data, and secondly, it follows with theory and the expectation very, very well. Just a few fun facts. This strain that we see is actually equivalent to the change of the size of an atom over the Earth-Sun distance. Okay, that's roughly the meaning of a strain amplitude. The delta L is the size of an atom over an L of the Earth-Sun distance. This is what the strain of H 10 to the minus 21 roughly means. And the black holes were traveling at about 0.6 times the speed of light when they merged. And because you need so much energy to basically curve space-time, then at the peak power, this was 200 billion times brighter than the most powerful supernova for this gravitational wave. And if you look at the amount of energy emitted, total energy emitted in gravitational waves, which was estimated to be about 3 times the mass of the sun, 3 solar masses, then this energy is equivalent to the total output of all stars in our galaxy for 500 years. Okay, so if the all stars in our galaxy have to burn for 500 years to emit the equivalent of 3 times the mass of the sun. And if you want to turn it to more earthly things, then if you take a cookie and you take the energy content of a cookie, then you need the mass of 10 to the 13 suns worth of cookies, 10 trillion cookies, to end up with the same energy content as three solar masses. Okay, so that's a lot of cookies. Okay, and then this is another nice pictorial way of seeing it. So the delay between the detectors was about 0.007 seconds. This is corresponds to the light travel time between the two. And the size of the black hole, the radius of the black hole basically is about the size, conveniently about the size of Scotland, so which is where I am. So this is the upper end of the UK, covers almost all of Scotland, and so on. And the signal was actually emitted about more than 1 billion years ago. And 1 billion years ago, there was not even multicellular life. So there was something swimming in the ocean that may not have been anything resembling us on Earth at that time. And then it took its time to travel and come at the exact moment. So that was pretty cool. Okay, and this observation won the Nobel Prize. It won the Nobel Prize not just for evidence of gravitational waves, first direct evidence of gravitational waves, but also first direct evidence of black holes, because these two things were direct evidence of black holes moving around. Nothing else could explain it, and that merger and that ring down at the end was completely consistent with what they expect for a black hole. Okay, and so Ray Weiss, Kip Thorne, and Barry Barish won the Nobel Prizes for this particular discovery, which was excellent. But what's more fantastic is that about that same year, later, no, maybe earlier that same year, yes, exactly. In August 2017, we observed the first binary neutron star from gravitational wave signals as well. And here we see again the very distinct chirp behavior. You can see this low frequency, and then eventually whoop sort of behavior. Except this time, the frequencies go up much higher to hundreds of hertz, okay? And what's more fantastic is that not just this signal was very clear and very bright in gravitational waves, about 1.7 seconds later, we see that there is a signal in gamma rays, okay? So here we have two bands from Fermi GBM, two energies. This is Fermi GBM, which is gamma ray burst monitor. And they see the signal here, and they see very clearly, much more clearly, the signal here. And not just in Fermi, but also in Integral, which is another gamma ray burst, gamma ray observatory, excuse me. They see a peak as well, and it all corresponds to roughly to about 1.7 seconds after the binary neutron star merger, okay? And this caused a lot of excitement, and everyone wanted to figure out where in the sky this was. And so here's another reason why we need to have multiple gravitational wave detectors. When you have multiple gravitational wave detectors, you can use it for localization, because we know that the light travel time, the gravitational wave time between one detector to the next detector should correspond to the speed of light. Then we can use this information about when they arrive to triangulate, if you like, the location of the sky location of the source. So in this sort of animated example, here's one binary. It travels here in these two different times. Sorry, let me just go back again. So it goes to the Livingston detector first, and then to the Hanford detector. And then on the different part of the sky, here it goes to the Hanford detector first before going to the Livingston detector, right? Because it's this part of the sky is closer to Hanford than it is to Livingston. Okay, so this time delay and other phase information from the gravitational wave detectors allows us to basically rapidly figure out where these sources come in the sky. Now, there are still very poor localizations compared to what you would expect for EM sources and so on, but for this particular source, we got very lucky. So here's the LIGO-Virgo localization of that source, which is this green thing here. The GRB observations, because it was only observed by the burst monitors, was relatively large, which is here. And then between those two, the telescope started to scan this region and very quickly found an optical counterpart in that small location there, okay? So they found an optical signal in this galaxy called NGC 4993, and they saw it like this. So here are the optical counterparts, which are observed. This transient here. Here you can see all the transients in different bands, optical bands, But you can see that, so sorry, let me just talk through this table. So this is gravitational wave observation, first observed here. And then 1.7 seconds later, you have this gamma ray observation. And then they found the optical observations with this, which is this transient here, okay, followed by infrared and so on and so forth. And then eventually the X-ray observation showed up, and even later, slightly later, the radio observation showed up. So this is VLA with the radio transient, and Chandra with the X-ray observation here. Okay, so this is truly a multi-messenger, because it's multi-band and gravitational wave observations, was a fantastic event. And because it was observed, let's look at the timescales here. It was 10 to the minus 2 days, 10 to the minus 1 days, 1 day, and 10 days. So it's on a log scale, but it was observed in so many timescales that you could see a lot of things happening. And why do we want to see a lot of things happening? Well, this is a cartoon taken from Fernandez and Metziger, this paper, very nice cartoon. And what we expect from a binary coalescence, right? So this is the gravitational wave signal, the binary neutron stars come together, and then you could have short gamma ray bursts, you could have X-rays emitted. We didn't actually see the X-rays emitted, the prompt X-rays emitted this time. It was actually the late shock X-rays, which is interesting and actually points to some interesting signs. Sorry, I need to go back, which I can't really go into too much detail here, but that's an opportunity for the future. But also you can see that there are UV, blue, red optical bands. This is the kilonova signal that we talk about, and then observations in the radio band, radio transients, and so on and so forth, and also late X-ray transients. So we want to observe, and these timescales again, these timescales are milliseconds, right? All the ways to days, to months, to years, okay? And that's why we need to observe on very many long timescales, first very promptly, and then on to continuous observations, because these tell us a lot of things about what's going on in the central engine of this gamma ray burst, about what's going on, of how the binary, well, they can tell us about the properties of the neutron stars, but they can also tell us about what's going on after the neutron stars merge, and so on and so forth. So here's an animation of what happened. So two neutron stars, they went together, and then they go faster and faster and faster. So the gravitational wave signal goes faster and faster and higher frequency. And then eventually they touch, and here's the gamma ray burst and the shock. And then here's the blue kilonova, the blue light, and then it slowly cools and then becomes red, as you can see. And here's the shock that is eventually observed from radio and X-rays, okay? And here again, this is the artist's impression of what's going on. Of course, we didn't actually see this by eye. Although we saw something, I'll show you in a moment, we saw something very close. So this is the gamma ray burst, and then here's the blue kilonova cooling off to become reddish and yellowish and so on and so forth. But here is the afterglow, the radio signals later on. But what I really like about this is that so they kept monitoring this signal, this galaxy, because of the very interesting nature of this source. So here's NGC 4993 as a reference image that many days before, many years before, okay? And then you can see almost in real time the cooling. I think I hit go, yeah. So it goes blue, and then it goes, eventually goes red, right? It starts to redden. And this is the spectrum taken in times now of sub-days, okay? And so you can see in almost live action, the cooling of that material of the ejector from that particular source, which I think is really, really cool. And this was done by the ESO, the European Southern Observatory. Okay, right. So one of the other things, I think I'm running out of time. I'm sorry, I've probably gone a bit too long. But just very quickly, one of the things you can do with these observations, apart from learning about neutron stars, is that if you have the host galaxy, which we do, which is the NGC 4993, then we have the redshift associated with that galaxy, okay? And in gravitational waves, because we measure amplitudes, then we actually only measure mainly the distance to the source. And so we have a redshift and we have a distance, and then we can put that and estimate Hubble's constant. And this is what was done. And this is basically our measurement of the Hubble constant, this broad probability distribution here, from that one event. Okay, and you can see that it's somewhere in between the Planck and the Schu's estimate. So Planck could be the cosmological estimate, and Schu's would be the supernova estimate, and we are somewhere in between. And of course, as we see more of these kinds of events, this distribution will get narrower and narrower, and so maybe one day we can sort of provide a link between these two observations. And as I mentioned before, when we basically, it's akin to particle physicists smashing electrons or protons together. Here we have neutron stars, we're smashing it together, and we're seeing what's going on inside the neutron star. Okay, so this is what's called, we can, from looking at the gravitational waves and the stuff that comes out afterwards, we can learn something about neutron star equation of state. The stuff that comes out afterwards, the ejecta, goes through this process called R process, rapid nuclear synthesis. Hello, yes?
You have 5 minutes.
Okay. Yes, I'm sorry. I realize I'm taking a lot of time, but this is almost done. I hope I give you enough time for questions. Okay. But one of the funny thing is that our process leads to the creation of gold, and actually, I think from 1708-17, about the equivalent of 3 times Earth in mass of gold was generated from that particular event. And then there was this paper that had this title with this graphic called Cosmic Gold, which was quite funny. Okay, so where are we now? What I just talked about was the first detection, which is 01 here, the first observing run, and 02, which is the second observing run, and this is 1708-17. Okay, and we finished 03, which is the third observing run, and we're actually in the middle of the fourth observing run. And we can see that now we have about 90 detections. So, sorry, if you count across here, you'll find that there are 90 gravitational wave detections. The majority of them are black holes, and so that we observed one more binary neutron star, which is 1904-25. This is a lot of information. I won't go through all this information, but I just want to highlight that we observed one more binary neutron star, but that neutron star was very far away, and localization, the point where it was in the sky, was not very good, unfortunately. So we didn't actually see very much in the electromagnetic spectrum associated with this binary neutron star. We saw a very heavy black hole. We saw a black hole that was formed that had more than 100 times the mass of the sun. So we know supermassive black holes exist. We know stellar mass black holes exist, but this is the first direct evidence of what's called intermediate mass black holes. Black holes that are within 110,000 solar masses, okay? And this was the first direct observation of the proof of existence of intermediate mass black holes. And also we've seen neutron stars merge with with black holes in binary, so we had events that are this. But it'd be nice if we had another neutron star that was observed in gamma rays and so on and so forth. I'm sure that many people would also be very excited about this. Okay, I can talk about the event rate, but maybe that's too technical for this point. But basically, we now see 90 events in total, and we are observing even more. And this event rate comes from the fact that we are increasing in volume over time. Okay, so every time we increase our sensitivity by a factor of 2, we increase our range by a factor of 2, but we increase our volume by a factor of 2 cubed, which is 8, which is roughly a factor of 10. So increasing a factor of 10 will basically give us a factor of 1,000 increase in amplitudes, which is why our event rate looks like this, because the detectors are becoming more and more sensitive. Okay, and the fourth observing run, we're actually in the middle of the fourth observing run. We are here now, 2024, and LIGO has been observing for the last few months, and here it says LIGO has already observed in the first half of the fourth observing run, 80 significant detections. So we have roughly 80 events, and those 80 events are most likely all black holes, unfortunately. Some of them are black hole neutron stars, but none of them are very None of them are binary neutron stars, unfortunately. You can verify this. You go to the public event database here and have a look. And if you actually the predictions, we are hoping that we can see many more binary neutron stars because we can see that even at the minimum we expect about 10 neutron stars, but we haven't seen any yet. So the cosmos is being a bit funny at the moment. But we're seeing a lot of these guys, a lot of the black holes here. It's consistent with this. It's very low on this, and maybe it's just we are being very unlucky at the moment. Okay, so gravitational waves is very good for fundamental physics, astrophysics, and cosmology. I will come back and I will leave this up in a moment, but I just want to say that for those who are interested, if you go to www.ligo.org, you can look for these science summaries, which are basically um, um, rewritten versions of our publications for a more general audience. So if you find the publications too technical, you can have a look at these science summaries. You can go directly to the publications. So if you go to this site, PMP papers, you can find a list of all the publications. Okay, and here is the Open Science Center, which I think Shushan will talk to you about more later. But you can actually go and download and play with gravitational wave data from the Gravitational Wave Open Science Center. So I will stop there. Sorry for going so long, and I hope I have left enough time for questions. Thank you.
Thank you very much, Professor. Are there any questions from audience? Okay, one question.
Greeting, Professor. I want to ask a general question here. As we know that gravitational wave can distort the space time, does it affect the space time or any event of the universe temporarily or permanently? And another one question is, I think it can distort the space and time. If so, it can possess a large amount of energy. How can we find the energy of the wave, and does it have any frequency range? Thank you.
Okay, so to answer your first question, actually, yes, the gravitational waves can distort space-time, let's not say permanently, but for a very long time scale. Okay, but these distortions, we call them memory effects. It's like an offset, and it may slowly change over time, but certainly not in the observation time. However, these things are considered to be very low frequency and not observable by LIGO. And in fact, they're very difficult to detect because they're so low frequency. On the other hand, you would think that is a problem because we have all suddenly shifted a little bit somewhere. But don't forget that it takes a lot of energy to change space-time, and these changes are 10 to the minus 23 or something like this, okay? Or even smaller. And all it needs is another gravitational wave to come along, and it will change it in another direction. So eventually, it could become just sort of, you could take the central limit theorem, and it comes all back to normal to average out to zero. The second question about the energy of gravitational waves, you can actually measure the energy of gravitational waves. So we did not directly measure the energy of the gravitational waves, if you like. We inferred the energy of the gravitational waves here in this signal because in the first detection, for example, because we know the mass of the object that was formed, which was 3 times less solar masses than the two objects that formed it. And if the two objects are black holes, which they were, then the energy can only be radiated as gravitational waves, okay? And so that's how we estimated the energy of gravitational waves in that situation. There are ways of measuring energy of gravitational waves. In fact, you can use a big piece of metal and try and measure energy of gravitational waves, like a calorimeter. But that's very difficult, again, because it deposits a very small, an extremely small amount of energy in the of gravitational waves. So it's very difficult to measure directly gravitational wave energy. Yeah.
Are there any other questions? Okay, I see there are no more questions. So we should thank Professor Siong Heng, and we are also expecting your in-person talk if you have time.
Yes.
to visit here in Nepal. Once again, thank you very much.
Thank you. Yes, I hope to come in the future. Thank you.
Hello. Hello. Sound.